This is an exam question that I especially like because it requires you to sort out what's important from what's not important. The text here reads that water is pumped from a reservoir to a large receiver vessel which is maintained at 6 bar or higher through the operation of a pump and a high pressure nitrogen supply that bleeds into the tank through a regulator. So water is coming from this reservoir over here through the pump, and it's going into this tank, and this tank is going to be at 6 bar or higher, and this nitrogen supply is going to keep it at 6 bar even if the pump shuts off for a while. So that's good. The water enters through an opening at the top of the vessel. Water's pouring in here, and there's nitrogen in there at 6 bar. A drain is provided at the low point in the system. So there's a drain here. And normally that valve will be closed because you won't be draining the system. So that's really not important to what we're trying to find out, I don't think. Elevations as shown, and we've got various heights and drops and so on. All valves are gate valves except for the swing check valve immediately downstream of the pump. So there's a swing check valve right here. The pipe is 2-inch galvanized iron with an inside diameter of 49.3 millimeters with screwed connections and a total length of 45 meters from the reservoir to the vessel. So the question then is, what head rise across the pump is required to deliver a flow of 0.01 cubic meters per second from the reservoir to the receiver vessel with the conditions as shown? Well, as shown, there's 6 bar in this tank. There's 4 meters of elevation above the pump. And presumably there's nothing coming out of the drain here. It doesn't really matter to us how much is coming out of here because this nitrogen is going to maintain that pressure at 6 bars, no matter how high or how low this flow is going out of here. So really, we can sort of ignore that part of the problem. So it's very much a matter of picking the points where we'd like to write our Bernoulli's equation. Points we'd always like to pick somewhere at the beginning, somewhere simple where we know what's going on, so that's location 1. And at the end, somewhere simple where we know reasonably well what's going on. If we pick this point, we'll have a velocity of 0, but we'll have to allow for the fact that the water's falling, looks like 8 meters from here down to the surface. And gravity and Bernoulli, and our life would just get a little more complicated. So let's pick this location as our second location. If that's location 2, then we don't need to worry about anything that goes on downstream here. And we know that location 2 is at 6 bars in this nitrogen-filled tank. We know that the velocity coming out here is whatever the velocity is in the pipe, and that'll be determined by the specified flow rate. So now that we've set up the framework for our problem, let's try and get some of the details sorted out. So first off, this is a galvanized pipe. It has a diameter of 49.3 millimeters. It also has a roughness height, referring back to the tables, of 0.15 millimeters for galvanized pipe. And what else do we need to know about it? We need some K values for our various components in here. So let's add up all the Ks. Starting from the beginning, we've got an entry there. It's a reentrant entry. And so that's going to be 0.8. We've got gate valves, 1, 2, 3 gate valves. And we've got a swing check valve. And we've got 1, 2, 3, 4, 5 elbows. And we've got an exit here. So if we go to our textbook, on this page we've got values for all of the elbows, T's, valves, and so on. And our gate valves, fully open, are going to be 0.15 for a K factor. Our swing check valve, if the flow is going forward through it, which is the way we want it, is going to be a value of 2. It would be infinity, i.e. there's a large resistance going backwards. And up here, for our elbows, this is threaded pipe. So either it's a regular elbow at about 1.5 or a long radius elbow at about 0.7. Let's take the 0.7 value. So the 3 gate valves at 0.15 for each of the gate valves. So that's times 3. 1 swing check valve at 2, and our long radius but threaded elbows, we said we're going to be 0.7 times 5. And finally, our exit will be a value of 1. And if we sum all of that up, what do we get? .8 plus 0.15 times 3 different gate valves plus 2 plus 0.7 times 5 different elbows plus 1 is 7.75. So that's the sum of all of the K factors. Now we're also told already what our flow rate is, so we can figure out the velocity. Velocity is Q over A. That'll be 0.1 over pi d squared over 4, and we know the diameter is 49.3 millimeters, so we better make sure we use 0.0493 meters in our calculation. And when I punch the numbers through for the velocity, I get 5.24 meters per second. Now, if we want to go on and get a friction factor, we're going to need a Reynolds number. So, Reynolds number, velocity times diameter divided by kinematic viscosity. This is water. So, kinematic viscosity, 1 times 10 to the minus 6 meters squared per second. Punching in the numbers, I get a Reynolds number of 2.6 times 10 to the 5th. I don't need an especially accurate answer, especially precise answer here, because I'm just going to use that to go into the Moody diagram. To get a friction factor, I also need to know a relative roughness. And that'll be 0.15 divided by 49.3. And if I punch that through, I get 0.003. Again, I don't need to be terribly precise because I'm just going to go into the Moody diagram on that one. So now, going to the textbook, making sure I get the right values from the Moody diagram. (10 to the 5th), 2 times 10 to the 5th, 2.5 times 10 to the 5th, there's about 2.6 times 10 to the 5th. And I go up here, and that's about halfway between 0.002 and 0.004, so that's about 0.003. And if I follow that line across here, over to there, I get about 0.026 for a friction factor. So that's the accuracy of the reading I'm looking for. If I get 2 significant figures, I think I'm doing pretty well. So F equal to 0.026. Now you'll notice we haven't actually done much towards solving the problem yet. We're just doing all of the accounting to find out what the piping system actually looks like and what the flow condition actually looks like.